YouTube, this is Umils03. In the previous lesson, we started talking about different primitive data types, right? The idea that int and double are not the only two primitive data types that represent numbers. And we can also think about longs and shorts and floats. And we said that longs are like ints, but basically they're characterized by holding a lot more bits in Java. So they take up a lot more memory, which allows them to hold much larger numbers, okay? And shorts are on the flip side. So shorts can hold much smaller ints, but on the flip side, they take up a lot less memory in Java. So anyway, what we're going to do is review some of those fundamentals in this video. But I wanted to do one more review of the two-dimensional array techniques that we were talking about in some recent videos, right? We were talking about how you could add two matrices together, how you could subtract two matrices, how you could find the transpose of a matrix, and also how you could determine the determinant of a matrix. And so we're going to see some brief examples here. So we have two one-dimensional arrays of strings, right? And so we're going to have hot dog, butter, September, and flagpole in the first string array. And then in the second string array, we're going to have tennis, cactus, August, and tablet, okay? And then we're going to create a two-dimensional array of string objects where the first one-dimensional array is going to be words A1, so this first array, and the second one-dimensional array is going to be words A2. And then we're going to create four one-dimensional arrays just with two elements, two strings in each of them. So the first one is going to have dog and cat, the second one is going to have hot and cold, the third one's going to have happy and sad, and the fourth one is going to have dry and wet. And then we're going to create a two-dimensional array called matrix B of string objects, and it's going to have those four one-dimensional arrays in it. But then we're going to say matrix B equals example.transpose of matrix B. So it seems like the transpose method belonging to the example class would have to return a two-dimensional array of string objects because we're assigning matrix B, which was already declared as a two-dimensional array of string objects, to the result of the transpose static method, which is provided in the example class. And it seems like it also accepts a two-dimensional array of string objects in addition to returning it. So what we can do is take a look at this transpose method that I have here. So I have a two-dimensional string array called result, and it's just going to be initialized to a new string array with empty strings in it, right? And so the number of rows is going to be array of 0.length, and the number of columns is going to be array.length. But what you have to think about is the dimensions are changing. So if you had like 5 one-dimensional arrays of 8 elements, then your transpose is going to have 8 one-dimensional arrays of 5 elements. So hopefully that's clear to you. And then we declare two ints on this line, right? Int variables. And then we initialize one of them to 0. And then we basically have a nested do while loop. So we can say do b equals 0. And then within that do result of AB equals array of BA, and then B plus equals 1, while B is less than the result of 0.length, and then A plus equals 1. And then in the outer do while loop, we say while A is less than result.length. So here A is the index position for which of the one-dimensional arrays that we're on, and for the result. And B is the index position for within those one-dimensional arrays, right? The particular string object result of A, B. So B is sort of like the string, and A is more the one-dimensional array within the two-dimensional array. But then anyway, we could return the result. And then anyway, while we're here, we also have a similar determinant method that we had to what we had in the previous video or 2 videos ago, right? Where we said if we were passing in a two-dimensional array of ints, we could calculate the determinant by doing basically here matrix of 0, 0 times matrix of 1, 1 minus matrix of 0, 1 times matrix of 1, 0. So it would essentially be the top left element times the bottom right element minus the top right element times the bottom left element. And that's valid for a 2x2 array, basically you would have two one-dimensional arrays, each of them having 2 elements in them. But here we can do it for strings. So we can return matrix of 0, 0.length, right? Because each of the elements in this two-dimensional array is going to be a string. So we could call the instance method length on each of those string objects, right? And just do the length of the top left word times the length of the bottom right string, right? Minus the length of the top right string times the length of the bottom left string. So hopefully that's clear to you. And then we also talked about adding two matrices together, two-dimensional arrays together, right? And so we could do that with strings too, or we could essentially, instead of adding numbers together, we could concatenate strings together. So we could say that the two-dimensional string result here is that new string would be a.length and a of 0.length. And we could have another try-catch block that we had in the previous video, right? We say try for int w equals 0, w less than a.length, w plus equals 1, and then within that for int x equals 0, true x plus plus, if x is greater than or equal to a of 0.length, so if we go out of bounds, break. But then otherwise we would come down here and say result of wx equals a of wx dot concat of b of wx, or you could just say a of wx plus b of wx, because we said that the addition, the plus operator between two string objects, just concatenates the strings, just combines the characters. And then within the outer for loop, but outside of the inner for loop, you would say system.out.println of arrays.toString of result of w, okay? And then you could also catch an index out of bounds exception if these two-dimensional arrays had different dimensions. And then we could have a finally block where we could say end of function prints regardless of exception results. And then anyway, we wanted to try this out. So we said matrix, so we had a two-dimensional array of one-dimensional arrays, right? And then we had this string, this two-dimensional array of strings, and another two-dimensional array of strings. But then when we call transpose, the rows become columns and the columns become rows. So instead of having 4 arrays with 2 elements each, we're going to have 2 arrays with 4 elements each, right? The first one is going to be dog, hot, happy, and dry. And the second one is going to be cat, cold, sad, and wet. After calling example.transpose of matrix B, and then we could print the concatenation of the result of matrix A and B. So anyway, if we go ahead and run it, we would want to go ahead and run where did I do this? I think I maybe just did then the matrix function. I think I called this the wrong thing. So we would just call this matrix function. Okay, and I guess the terminal window is escaping me again, but we will go ahead and see that all of those strings are concatenated together, and we can compare it with what we were expecting here. So essentially, the hot dog is being concatenated with dog, right? And then the butter would be concatenated with hot, and then September is concatenated with happy, and then flagpole is concatenated with dry, because we took the transpose of the second matrix. So hopefully that's clear to you. And then in this video, I wanted to talk a little bit more about these other types of primitives. So we can think about a static method within our example class called number function. And we could say that an array of strings, giant labels, would just be largest long, largest int, largest short, just 3 strings. And then we're going to have an array of longs. So this is an array of a new primitive that we've been studying. So remember, longs are characterized by having a lot more bits, right? It's a lot more zeros and ones to represent them in Java. But then on the flip side, the good thing about them is they can store much larger numbers as a result of that. And so the first element in this array of longs would be long.max value. So one of the things I think we did in the previous video is we studied the API. So we go to blackhole.com and then we type in long Java API and click on the first result. And you see that the long class provides a constant called max value, and it's 2 to the 63 minus 1, which is by far the largest value that Java can hold. I guess if you did 1 less than that or 2 less than that, you could do that, but it's a hell of a lot larger than integer.max value, right? The largest value of an int, which in turn is a hell of a lot larger than short.max value, which is the maximum value that a short data type can hold. So anyway, we can go ahead and compare the console output, which again, I don't know why it keeps escaping me here, but we're going to go ahead and compare the code that I wrote to the output here, okay? And so what we're going to do is we're going to create a hash map. So we're going to create a dictionary, and the keys are going to be strings and the values are going to be longs, right? These long integers, which are characterized by holding a lot more bits, right? And then we could say my dictionary equals new hash map of string and long. So again, the keys have to be strings and the keys have to be unique, but the values are longs and they don't have to be unique, right? You could have 2 different strings that potentially have the same long that they map to, okay? But that doesn't But okay, so here what we're going to do is we're going to say for int p equals 0 true, p plus equals 1. So presumably this is a loop that we could only break out of if we had a break statement, but we're going to say my dictionary.put of giant labels of p with giant numbers of p. So giant labels of p is going to come in as a new key for each value of p, and giant numbers of p is going to come in as the corresponding value that's associated with that key. And then we could say system.out.println of giant labels of p concatenated with a colon, and then my dictionary.get of giant labels of p. Okay, and so that's what happens in the first three print statements here. So we're essentially saying largest long, and then we have the value of 2 to the 63 minus 1. And then we also have the largest int, so that's 2,147,483,647. And then the largest short is only 32,767, but that's the effect of these two lines of code. And then in this architecture, we say if p is not equal to giant numbers dot length minus 1, right? So if p is essentially not the last index position, the last valid value that it could take without having an index out of bounds exception, we're going to continue, right? So if p is not equal to 2 essentially here, right? Because these arrays have 3 elements in them. So if p is not equal to 2, we want to continue, which means that we're going to end the current iteration of the loop. So that means we're not going to hit the break, right? But if p does become giant numbers dot length minus 1, we don't continue. So that means we would go down here and break out of the loop. And so that is successful loop termination. And then we could say, is it still large if we divide the largest long by 2 and then subtract the largest int, right? That's what shows up here. And that's what I did. So I said system.out.println of my dictionary.get of largest long over 2. So that will give us the value associated with the key largest long. And so that would be long.max value. That would be this giant number that was first printed on the console. But that divided by 2 and then minus my dictionary.get of largest int. And we could see how large of a number this would be. And that's still an insanely large number. And it just comes to show you how much larger the maximum long is than the maximum int. And then you could say try system.out.println of short.decode of 50,000. So presumably there's a method called decode that belongs to the short class, maybe a static method that accepts a string. And it seems like it would return something. But anyway, we can go ahead and study that, right? So we could say short Java API, and it wraps a value of primitive type short, just like an integer wraps a value of primitive type int, just like a Boolean with a capital B wraps a value of primitive type Boolean with a lowercase b. But the point is that we could scroll down and we could say, which method are we looking for here? So we're looking for the short.decode, right? So essentially what we could do is study the API, and it says that it decodes a string into a short, and it accepts decimal, hexadecimal, and octal numbers given by the following grammar. But the point is that you would have to accept a string into it. So you would accept a string, and that might be why they say NM here. But the point is that it has to represent a number. But the problem is that if you remember from when we were looking at the terminal window, the largest value of a short is 32,767. So there might be a problem here. And so if we catch an exception, we could say system.out.println of shorts cannot hold values that large, I should say that large. Need to accept a string representing a smaller number. Okay, so you can just replace the word long with large here, but shorts cannot be 50,000. They can only be 32,767 or smaller, right? And then so clearly short class provides a static method called decode that accepts a string object. And so we print that regardless because that's in the finally block. So hopefully that's clear to you. And then we could say long q equals new long of negative 277, y equals new long of math.apps of negative 19,000. So this declares and initializes two long objects on the same line. And it also makes a call to the ABS, the apps static method of the math class, which, as we talked about in a previous video, accepts an int or potentially a float and returns the absolute value of it. So here it would be 19,000 would be the long number that's being wrapped by the variable y. And then we could say my dictionary.replace of largest int Q, Y. So what we could do is we could go ahead and remind ourselves of how the API for the HashMap class works. And so basically the way that it works is it has an overloaded replace method. So there's a couple different versions of the replace method, but what we have to do is study the one that has 3 arguments, right? I'm calling the one that has 3 arguments, largest int, Q, and Y. And it says that it replaces the entry for the specified key only if currently mapped to the specified value. Okay, so is largest int, is that string currently being mapped to -277? No, it's not. So it's not going to make that replacement. And so then we could go ahead and say system.out.println of mydictionary.get of largest.concat of I, capital I, dot 2 lowercase plus nte dot substring of 0, 2. So here I'm just practicing on some more methods from the string class, which we discussed in lessons 5 and 6 at great length. But the point is that this would form largest int. It would form the same key as you see here, because this would become a lowercase I, and then as a result of calling dot substring of 0, 2, we would only get the n, and t. So we would just get largest int. So hopefully that's clear to you, but we can go ahead and pull up the terminal window, which always seems to escape me. So we're going to say that we could just print the same value of largest int that we fed into it at the beginning. It didn't get replaced because the value originally was not Q, it wasn't -277. And then we could say mydictionary.put of dog and Q. So it's just going to create a new key value pair, right? The keys have to be strings and the values have to be longs. Okay, and then now we're going to create a dictionary, another dictionary. And so we could say hash map of string long. So it's going to have the same data type for keys as my dictionary did, and it's going to have the same data type for values as my dictionary did. But we're going to call it cookie, and we're going to say that it's equal to a new hash map of string and long. And then we're going to say cookie.put of tree with Q plus 2. So that would be like -275 would be the long that's assigned to the key tree, right? And then also -275 would be assigned to dog. So then what does the put method do, right? So then essentially what we could do is go ahead and see the put method, right? And so it says if the map previously contained a mapping for the key, the old value is replaced. And so that would be the effect here. So now dog, instead of being mapped to -277, it's going to be mapped to -275. And so we would see that if we said mydictionary.putAll of cookie. So now there's another method that belongs to the HashMap class. It's kind of a bonus one that we can look at here that I probably didn't discuss in a previous video. But again, if you're looking at the HashMap Java API, you Google it and it tells you the different methods that you can do with a map, the different methods that you can do with a dictionary. Okay, and so you would go ahead and see the putAll method. It's a void method, so it doesn't return anything, but it's an instance method. So you just call it on a particular instance of the HashMap class. You call it on a HashMap and you say for that particular HashMap, hashmap.putAll of, and then you have to feed in one more. You have to feed in one argument. So you feed in another hash map, and basically what it does is it copies all of the mappings from the specified map to this map. So just all the key value pairs that were in the dictionary that you passed in are going to be fed in to the dictionary that you called putAll on, right? And these mappings will replace any mappings that this map had for any of the keys currently in the specified map. So hopefully that's clear to you, but that's what would happen, right? Because if we say cookie, I guess what we were saying earlier, I guess I got confused because we said that put would replace the value for a specified key, but that's not what's happening here because this is a different dictionary. Okay, so dog is getting assigned for the first time, but what we're saying is that as a result of calling putAll, the value associated with the dog in my dictionary is no longer going to be -277, it's going to be -275. So it still gets replaced with the value that was assigned to the dog in the cookie hash map. So hopefully that's clear to you. But we could say mydictionary.putAll of cookie. Again, it doesn't return anything. You just call it. It's a void instance method that you call on an instance of the hash map class. And remember, you have to go ahead and import these classes at the top. So any classes that you want to use, if you're talking about a hash map or a collection, you would need to go, or if you want to use static methods from the collections class, you need to remember to import those, right? But then you would say for each of the string S, for each string S in my dictionary.keyset Okay, and so you can reference each of the keys, each of the keys in the set of keys for your dictionary, and then you could say system.out.println of key colon, and then basically s, and then that would be your key, right? And then value, and then my dictionary.get of s. So that would give you the value that's assigned to that particular key. And you could say key tree, value -275, key largest int, value 2,147,483,647, right? And so it just gives you the key value pairs. And we said that sets are characteristically unsorted. So that's why these do not show up in any particular order. But we'll be reviewing these fundamentals in the next video, talking a little bit more about vectors and then just talking about some more fundamentals from there. From UMills03, thanks for watching and please subscribe.